Hello, everyone. I'm Ryan Keeley, currently working as a postdoc at UC Merced. So first, I'd like to thank the organizers for putting on this conference and you all listeners for your attention. So I'm interested in testing all parts of the Lambda CDM model and developing statistical tools to do so robustly. So from dark energy to inflation to general relativity. But today I'll have my dark matter hat on and tell you about how to test the CDM part of Lambda CDM. So dark matter structure exists on all scales of the universe, from galaxies and clusters, where it was first discovered, to the entire observable universe, and large-scale structures, where the density of it is measured, and it's on the smallest scales where the most novel tests of dark matter occur. So specifically on 10 to the 6 scales, where we expect to find dark matter halos that are completely dark, as in where galaxies and stars will fail to form efficiently. So there's a range of astrophysical probes of dark matter as listed here. And so they all tend to test dark matter in rather phenomenological ways, as in rather than testing a specific identity of dark matter, they test whether dark matter, say, self-interacts or how it clusters. Indeed, most of these tests of dark matter work by trying to identify what is the smallest dark matter halos. And so in this talk, I'm going to elaborate on how to use strong gravitational lenses to characterize the population of the lowest mass dark matter halos and hence constrain dark matter particle physics. Uh, so one common way to summarize the dark matter physics that can be probed are shown in these sorts of dark matter figures of merit. So broadly, astrophysical probes of dark matter seek to answer questions like, is dark matter really cold? Is dark matter really collisionless? This gets translated to is the number of dark matter halos suppressed with respect to CDM, and are the profiles of dark matter halos different than NFW profiles? So there's many Lagrangian level dark matter halos that can make predictions with respect to these questions, but it's common to simplify the model landscape into these two parameters. So the mass of a simple thermally produced warm dark matter particle and the cross-section of an SIDM particle. Many models map onto the predictions of these representative models, which is what makes them representative. So I'm going to focus on warm dark matter in particular for the rest of the talk, since it's one of the simplest cases for dark matter that we can test with strong gravitational lenses. So where CDM predicts an abundance of dark matter halos at small masses, warm dark matter predicts few. So it's the free streaming of the warm dark matter particle that suppresses structure at small scales. So to find what scales are suppressed, the general idea is to constrain warm dark matter by finding the smallest dark matter halo. So typically, warm dark matter has masses on the orders of keV, and common examples of warm dark matter are, say, the sterile neutrino. So it's in strong gravitational lensing, the light from a background source is deflected by the combined gravitational potential of a main deflector lens and all of the subhalos and line of sight halos between the source and the observer. So this deflection creates multiple images of the source. So strong lensing probes dark matter. These work by analyzing the additional magnifications and distortions of images to reconstruct or infer what is the distribution of matter. So the deflection is determined typically by the first derivative of the gravitational potential, which is in turn determined by the image positions. The magnifications are determined by the second derivative of the gravitational potential, which is why the fluxes are such useful probes of the clumpy distribution of low mass halos. So there's two common techniques for inferring dark matter from strong lenses, one that's called gravitational imaging and one that's called the flux ratio anomaly method. So gravitational imaging typically uses larger source sizes, which create extended arcs and look for dark matter by basically look for dark matter in the distortions and kinks and gaps of this extended arc. And so basically, this is working with the galaxy lenses. In contrast, the flux ratio anomaly method is used when looking at smaller source sizes, such that four distinct images can be created. So rather than an extended arc. So it's analyzing the fluxes of these images that can allow us to make inferences about the mass of about the mass function of low mass dark matter halos. And it's this technique in particular that I'll be focusing on for the rest of the talk. So the basic idea of this technique is that if you take the known large-scale mass distribution of the lens, aka the macro model, then you can make precise predictions of what the fluxes of the four images should be. Any additional low-mass dark matter halos will perturb the actual fluxes away from the prediction of the macro model of the lens, and this anomalous flux, as it were, is the signal of low-mass dark matter halos that we're looking for. In this method, we're specifically looking at the ratios of fluxes from these quadruply lens quasars rather than galaxy lenses, and we're looking at the ratio basically to divide out the unknown flux of the source of the source. Because we don't parameterize in particular the specific realization of dark matter structure in the plane of the lens or along the line of sight, instead the model predicts a distribution of fluxes, not a single value of the flux ratios. And so hence we need machine learning or simulation-based inference techniques in order to tease out the statistical signal. And it's the statistical signal that's shown here. So at the simplest thing you can see this plot down below is that the CDM predicts a much wider range of a much wider distribution of flux ratios than the warm dark matter model. Well, it's basically because the cold dark matter predicts a large number of low mass dark matter halos. There's a large number of specific realizations of those dark matter halos that can in turn produce a wide range of flux ratios. In contrast, the warm dark matter model predicts a small number of dark matter halos, and hence the scatter in what the warm dark matter predicts is much less. And so it's this difference in scatter and predictions between the two models that is the statistical signal that we're looking for. And so that's basically in turn what these plots are actually showing. These are showing the likelihoods of the two different models. So say if you were to say observe something that would be on the edge of the cold dark matter model, it's not in a particularly low probability region of the likelihood for say cold dark matter, say negative 1.5, 2.5 on the plot, but in turn it is in a very low probability region of the warm dark matter distribution. And hence, if you were to say observe an actual set of flux ratios in that region, then the cold dark matter model is preferred at say a factor of 100 or so to 1. And hence that's what a likelihood is. What is the probability of observing a certain certain set of data, in our case flux ratios, given different models. And so like I was talking about earlier, the source sizes of the size of the source of the thing that we're looking at matters. And for our flux ratio anomaly method, we're looking at quasars. And so different regions of the quasar will in turn give us different predictions for what the fluxes will be. So basically, because the smallest source sizes are the most sensitive to the lowest mass dark matter halos, we want to observe the smallest region of the quasar that we can without being microlensed. And so that turns out to be the warm dust region, which is on scales typically say 1 to 5 parsecs, which is in contrast to the nuclear narrowline region, which is on the scale of say 80 parsecs. And so you can see basically the difference in the percent of change of the flux. Basically, so if you were to imagine moving an individual subhalo across a specific image in a quadruply lensed quasar, what this plot is showing is the percent change in flux that you would expect between the two different regions. So the simple takeaway here is that the warm dust region at 5 parsecs is a much stronger probe of low mass dark matter halos than the nuclear narrowline region. So like I was talking about here, just to show you that's a cartoon of what I mean. The nuclear narrowline region is relatively big and hence is less sensitive to low mass dark matter halos. But it's specifically this warm dust region, what was previously called an obscuring torus region, that we're going to be looking at with our JWST images. So to walk you quickly at least through basically the data reduction from our JWST images. So basically the simple idea here is that we have to observe each of our lenses in 4 MIRI filters, basically in order to get at specifically the warm dust region. to get at specifically the warm dust region of these quasars. And so but each of the individual images won't necessarily will have not just the individual fluxes, the point sources that we're looking for. It'll have flux coming from both light from the lens itself and from essentially extended emission of different parts, basically from the host from the host galaxy of the quasar. And so we have to essentially model them out. As you can see in the residuals here, we can do so successfully. And so basically, because different parts of the quasar will basically emit in different filters, we basically have to subtract out basically like the hot dust region from the warm dust region, basically because this hot dust region is an even smaller size and it's microlensed. And so we want to get at specifically the warm dust region because it's basically in that intermediate region of, say, 5 parsecs, where it's both not microlens, but still small enough to be middle lens, to be lensed by low mass dark matter halos and not individual stars. And so basically, in order to get at specifically the warm dust region, we essentially have to model the SED from individual parts, specifically the continuum, the hot dust, and the warm dust. And like this figure shows, we can again do so successfully. So to summarize the whole sort of data reduction pipeline, you observe each of the each of our lenses with 4 JWST MIRI filters, 560, 1280, 1800, 2550. You model the data with point sources, lens lights from the quasar host galaxy, and then the deflector light. You can do that subtraction successfully, and then you can take those point source fluxes to the SED level, where you're essentially subtracting out a continuum and a hot dust component, and specifically using the warm dust fluxes of the point source component of the images that we're using for our dark matter inference. And so here I'm just going to define a few parameters that I'll be talking about later. So specifically, I'm going to be talking about the half-mode mass. So this is basically the scale where the mass function of dark matter halos is suppressed by a factor of 2. And the interesting part about this is that it's determined by the mass of the dark matter particle, as you can see in the equation here. And so it's specifically this mass function that we're going to be constraining, this half-mode mass, this mass function that we're going to be constraining with the data. So here I'm just going over a few of the sort of the technical details. So in general, we have a mass function which has various correction terms, which includes terms like this psi2 halo for basically correlated structure along this line of sight. We include basically this delta line of sight term, basically to account for the fact that the sight lines of strong lenses are typically over dense compared to a randomly selected line of sight. In general, the warm dark matter mass function is just the cold dark matter mass function multiplied by some suppression factor, which is given by these numbers here. And one complicating factor is that specifically the mass function of subhalos are different than the mass function of field halos, basically because they're going to be tidally disrupted. And so basically we have this additional parameter sigma sub to account for this fact. So the sigma sub is specifically the amplitude of the subhalo mass function, and the script F term is basically allows us to combine subhalo mass functions from different lenses because it includes the different scaling of different host mass and different redshifts. And so all of this sort of subhalo physics is basically calibrated with semi-analytic models like Galacticus. And so this takes us to our statistical method. So we're specifically using the approximate Bayesian computation method. And so it basically works by sampling the prior to get the parameters that we're interested in. You can use those parameters to calculate a mass function. Then you populate your lens you're looking at with line of sight and subhalos. And then you can calculate the ray tracing and do the lensing to calculate flux ratios. With the flux ratios, you can then do the actual ABC, start to do the actual ABC parts. You can calculate a summary statistic by how different these simulated or predicted flux ratios are from the data. And then if that S statistic is within some threshold, then you say it's accepted. And so the distribution of accepted parameters is then your approximate posterior. And we do so with the basically a list of open source software. Basically, Samana here is basically the thing that wraps this entire procedure. We use PyHalos to do the rendering of the line of sight and subhalos. We use Galacticus to model the subhalos, and we use Lenstronomy to do all the lensing calculations. And that brings us to our actual constraints. So basically here, this is the posterior that we calculate, and we can see that the half-bird mass of greater than 10 to the 7.6 is rolled out at odds of 10 to the 1. This corresponds to a warm dark matter mass of 6.1 keV, which is competitive with other techniques such as Lyman alpha forest and Milky Way satellite counts. So this constraint was specifically done with nine individual lenses, as you can see here. And this work is part of a larger JWST program that will observe a total of 31 lenses. And so the point is that you can expect this constraint to only improve as we finish up analyzing the rest of the lenses over the course of this year. And so that basically brings us to the summary. And I would just like to leave you with this last interesting point. So with our substructure lensing, we are directly observing dark matter. We are directly observing dark matter and characterizing the population of completely dark matter halos. And basically these halos have no corresponding galaxies, and so this is basically the only way that we can see and are seeing these lowest mass dark matter halos. Basically directly confirming the existence of dark matter. So thank you for your time, and hopefully you all have questions.